Hello, so this is going to be one of those videos where I really hope I can get things in frame properly, and it's going to be doing a comparison between a Victoreen 450 digital ionisation chamber and this GMC-500 Plus digital Geiger counter. And the reason is I kind of wanted to display the pros and cons of Geigers versus ionisation chambers with two that are kind of similar enough that, you know, it's a fair comparison. Because comparing like a Therapy or a GMC-500 against an old US CDV-700 isn't really fair, you know, just for the same reason it wouldn't be fair to basically compare, you know, something like this against an old CDV-715 or a 720. So what this is two sort of decent digital radiation detectors, a Geiger counter using a Geiger Muller tube to detect radiation, an ionisation chamber using a literal ionisation chamber, just a box that detects radiation essentially, or a sphere that detects radiation, however you want to do it on each counter, to detect radiation. So what we're going to do is I'm going to set this one to millirontgen per hour, because this one displays millirontgen per hour, and then hopefully what will happen is we can put samples on each and we can see how they are similar and how they differ. Because a Geiger counter is kind of a jack of all trades thing if it's giving a dose equivalent, because they're never as good at giving a dose equivalent because it's basically calibrated on a single source, normally cesium-137, which means they're either going to be higher or lower than that actual source in reality. So let's zoom in there. So hopefully we can see that this is saying 0.039 millirontgen per hour, and this is currently at 0.04. So that's not all that different, you know. The decimal place is in the same place, so we're not too far things, and that is closer to the radioactive sources, this ionisation chamber. So this isn't going to be completely scientific, of course, because the problem is that, you know, with each of these, you're always going to have things of some are closer to a sample. The Geiger Muller tube might be more of the shape of a sample or not the shape. So first we're going to use a Fiestaware dish. I'm sure you're pretty familiar with these. I've got the Geiger counters ticking turned off because otherwise it'll get very irritating. So what we'll do, we'll get the Fiestaware this way, we'll put the Geiger Muller counter on top of it, and we'll see what reading it gives. So I've got it set to the fast 10-second estimation on here. The reason being basically that 10 seconds won't be irritating to wait for it to give a reading, but it shouldn't jump around as much as 5 seconds. Obviously, if you want to do really accurate readings, you'd do it with 60 seconds on each, and you'd leave them like sitting on the sample for a minute and see what it kind of zeroes off at. But looks like we are getting about 1.8 millirontgen per hour. So, you know, it seems to be sitting pretty stably at 1.8 there. Going up and down a little bit, but in the 1.8 millirontgen per hour region. Right, now let's try that with the ionisation chamber. So I'm going to try and put it in the exact same spot. But that might be difficult, so hopefully the display can still be seen there, because as I said, this isn't a brilliant digital display in terms of clarity. Looks like we're at 2.0 at the moment, 2.1, 2.2. Ionisation chambers are a bit slower to go up and down, but in general they are more accurate once they sort of settle on a number. It's on 2.5, 2.4. So according to this, it is actually slightly more radioactive. And you might be saying, oh, that's interesting, why is that? Because, you know, in theory, Fiestaware is quite weak uranium emissions in terms of beta and gamma. So, you know, and it's probably because, although the Geiger counter is on cesium-137, this ionisation chamber is way more sensitive to actual air ionisation. It's got a very thin beta window and everything else. So although it's going down a bit again now, this is slightly more sensitive. So on this, the higher number comes from the ionisation chamber. So let's pop this back over there. Now let's just get some samples of Torbenite and Autunite. So what we'll do is we'll just take the lid off here. Obviously I want to do this without flicking little bits of radioactive crystal all over the carpet. There we go. And what we're going to do is just put this flat here. Now, which side has the more sensitive tube on that one? Right, if I can get it to flick the numbers back round. So this isn't all that scientific because I'm just basically laying it flat on a thing. Right, 4.5 millirontgen, 5 millirontgen, 6 millirontgen. It seems like it's going 7 millirontgen. So it's flicking, I guess, between 6 and 7 millirontgen in various degrees. Now, this is going to be harder to do because obviously some of those crystals are more active than other ones. But that was coming to about 7 millirontgen. Right, let's see what this does if we pop him flat on here. Right, very interesting, already at 67 millirontgen. So why is it so much higher? Basically because the ion chamber is much better at detecting ionisation of the air. 61, 64, 65. So yeah, interestingly, this is actually giving you a more accurate number, because what it's doing is it's measuring probably lower energy beta as well that can get through the bottom of this ion chamber, and it's basically how much it's just ionising the air inside an ion chamber. The really obvious way of telling how much better ion chambers are for detecting than Geiger-Müller tubes is basically using an open-air ion chamber with a americium-241 versus an alpha-mica Geiger counter, and notice how different, you know, how high the reading is comparatively. So yeah, that's 0 finishing off about 50 millirontgen. That's dropping a bit now. Let's drop to 30 odd, 40. But yeah, the point is this is giving a way higher reading, and I guess it's because the film on the bottom of here is quite thin. And this is just an open-air ion chamber. In theory, you could rip this open, of course. I'm not going to do that, and make it even more sensitive. But then you could, you know, risk getting contamination inside the ion chamber and giving false readings and all that. So far, this has been slightly higher and way higher. So let's get them back both in frame. Are they both in frame there? Just about. And let's get out some of the more interesting samples. So let's actually start off with something a bit boring, a thorium lamp mantle. The reason being that thorium lamp mantles, thorium is interesting because it's actually fairly high gamma energy that comes off of thorium, but Geiger counters can't obviously tell you how high the energy is. So they give kind of a falsely deceptive low reading with thorium. So let's see how these differ. So it looks like it's going just over 1 millirontgen, about 1.1, maybe 1.2. Right, so that's giving us an estimate of about 1.1 millirontgen, let's say, with that one. Now let's try the same thing with this. Let's see what happens. I'll get that flush on there. Hopefully the number will still be visible. It looks about 1.14, yeah, 15, 13, 15. So that seems to be settling around the 15 mark. I sometimes find this easier to use the bottom display to see what numbers it sits between. It's dropping off a little bit now, but you know, seems to be about 14, 15 odd on there. So that's interesting. So as you can see, thorium shows way more energy on an ionisation chamber. The reason being, it can detect some of the higher energy gamma emissions, I think mostly, that the Geiger counter can't. And as well, it's probably detecting the lower energy beta emissions that aren't quite managing to penetrate the glass Geiger-Müller tube on here. So right, that's very different. Right, let's go to one of our favourite bits, shall we? Strontium-90. We will use a good old Soviet bit of Strontium-90 here. So that's that one, if you can see it. Just about in frame. That's the one from one of the Soviet Geiger counters that's just had the foil removed from it. So right, we've put that directly on the GM tube. I'm using this bit of Strontium-90 because it doesn't overload this Geiger counter. The issue is some of them do. So you basically have it just stop reading at certain ranges because of the electrons overloading the thing. So let's see what it settles on. 5.9 millirontgen. That is pretty similar to the sort of 6 or so millirontgen it gets inside the probe of the DP5Vs. So that isn't too far off. So yeah, that's what you kind of expect that to read. Obviously, I can't remember, this isn't the same one that is in my DP5V, how energetic that bit should be, but that makes sense for sort of the age of it and the sample size. So, at least on a cesium-137 equivalent, 5 to 6 millirontgen. Right, now let's do him on here. So I'll try and get this in frame as best I can. I always hate the handles on these because they always get in the way. Right. It's already up to 10 millirontgen. Looks like it's sitting between 10 and 15 millirontgen. So interesting, again, something giving a higher reading on this. And I'm assuming it's just because the ionisation chamber is more sensitive to some of the lower energy beta bits. You know, so there's that. So Strontium-90, higher reading on the thing. If you want to see something really crazy, let's get the Chinese bit of Strontium-90 and just put that on top here so you can see how high it goes. 75 millirontgen. Not actually as high as one of the bits we looked at earlier, was it? But right, now for probably the most exciting and scary thing in the video. Let's get the good old what's it called out? The DP63 back screen. And yes, I'm going to give my hands a very thorough wash after this video because I'm not wearing gloves, but it's easier to handle it like this. So, I think you will know this apocalyptic monster by now, the back screen of a Soviet DP63 Geiger counter. So what happens when you put this on here? Pretty much cuts out the Geiger counter. We're not going to get an accurate reading on this using this one. I'm going to have to hold it about this far off. Because yeah, the issue with this is it's quite good at overloading Geiger counters, just due to the sheer amount of electrons coming off. But here's the interesting thing, this Geiger counter can only read beta and gamma. This is also giving off a lot of alpha radiation, and I think that's where the ion chamber is going to get a much higher reading on it. So this is saying about 20 millirontgen at this distance. Again, if you used a Tera-P, you can get over a millisievert easily with this. But anyway, let's now pop this one on top and get this one's reading. And look, woo, shooting up, straight up there. We're over 300 millirontgen. 330 millirontgen it seems to want to settle on for that. So there you go, 330 millirontgen. Now I'm sure somebody can do the maths, I can't easily in my head, and work out what 330 millirontgen is in millisieverts. Probably about 3.3 millisieverts if you didn't adjust for the like 0.4 on it. But yeah, 3.3, 3.4 millisieverts or 330 millirontgen. So yeah, pretty scary, isn't it, this bit of radium? But again, that's because it's also reading some of the alpha on it. So, hopefully you found this video interesting. I'll do it again with a Keithley at some point, but yeah, this is the reason I really like digital ionisation chambers, because they are really sensitive. And again, they get round the issue that old ionisation chambers had, which was that, you know, they just weren't sensitive enough. They had very primitive sort of electronics, whatever. But if I had the option between a digital Geiger counter and an ion chamber for taking proper readings, I would probably go with the ion chamber. Geiger counters are very good for being portable and compact, but ion chambers are brilliant just for measuring the pure ionisation of the air. Because what an ion chamber basically does is it has a box and it just measures the electrical interference, in a sense, the ionisation of the air inside its box or like chamber. Whereas a Geiger counter is basically using counts and then equating it to dose. So hopefully you found this video interesting. I'm going to go and very, very thoroughly wash my hands now because, you know, scary, scary radioactive sources. I suppose if you wanted to do something really funny, you could put a load of radioactive sources on here, then sandwich it onto the ion chamber and see if you can get it really high. Shall I do that as a joke just before I close the video? Yeah, let's do this to end the video then. So we'll put that there. Let's get all the scary samples back out and put them next to each other. The ones that are at least flat enough to fit under there. So what we'll do, we'll have the Chinese strontium-90, the Russian strontium-90, a thorium lamp mantle, and that bit of radium. And let's see how high it reads. So hopefully you can see on there, just on that dish, like a little dish of horrors. Let's put that on here and see what happens. Right, I'm not going to push it completely down because obviously I don't want to pierce the film, but what sort of numbers are we getting? That 240 millirontgen? That's not actually as high as it was in the other position, but that might just be whereabouts they sit on the ion chamber. Yeah, there we go, look, it's shooting up again. So there might be some spots in it that are more sensitive than others, but yeah, we're getting over 300 millirontgen easily doing that. And again, some of it's going to be more active than other bits, but yeah, just to show you the crazy sort of reading this gives, if I push that directly against it with my finger, 430 millirontgen, 450 millirontgen, 470 millirontgen. Oh, it goes to 0.5 rontgen per hour now, look. Just kind of interesting. If I can get that in frame. Yeah, so once you get to that height, it just goes to 0.5 rontgen. Pretty good calibrating display. So there's that. The Chinese strontium-90, if I hold it against it, will get a higher or lower reading. The only problem is it's going to, the sort of sharp foilness of this is going to pierce its foil. Oh, I can't see what it's reading, 77 millirontgen, so that's nowhere near as high. But yeah, there you go. Digital ionisation chambers, really cool bits of kit, especially if you want to read really high levels of radiation without them crapping out, unlike certain Geiger counters. But yeah, not as compact as Geiger counters, but you know, I have a soft spot for digital ion chambers, and we'll do a review of the Keithley at some point as well, using the same sort of materials. Probably won't bother directly comparing it to this one with the Keithley, but we'll just see sort of what numbers the Keithley gets with its beta and gamma readings on a lot of these samples.